Welcome. This review material will focus on calculations that arise when a weak acid is titrated with a strong base. Concepts covered include pre-equilibrium calculations, the 5% rule, the Henderson-Hasselbalch equation, various pH calculations, and other concepts as different amounts of strong base are added to a weak acid. So let's begin with a simple titration where given amounts of a strong base, sodium hydroxide, are added to a weak acid, acetic acid, and we are asked to calculate the final pH after each addition. It may help to first diagram the problem to assure you know what is given and what is being asked. So let's calculate the pH before any base is added. The first step is to write out the acid equilibrium, and it's a good idea to always write the Ka over the equilibrium arrows. It is worth mentioning that the small Ka value indicates the acid does not want to associate. In other words, the equilibrium will lie to the left because the conjugate base is unstable or high in energy and therefore reactive, or one could simply say it is a strong conjugate base. Thus, acetic acid is a weak acid. Remember that understanding acid strength is simply examining the stability of the conjugate base. So now let's also include the initial concentration of acid at T0 and the change in concentrations when at equilibrium. Now we can substitute the equilibrium concentrations into the expression for Ka. As is, this expression produces a messy quadratic equation, but fortunately there's an easier way to solve this problem via the 5% rule. The 5% rule works when the extent of ionization will be less than 5% of the initial concentration of acid. For example, we predict that acetic acid will dissociate very little due to the small Ka value, and therefore X will be small when compared to the initial concentration of 0.1 molar. Thus, the denominator can be simplified, which affords a much easier calculation. Interestingly, the 5% rule arises due to the fact that Ka values are known only to an accuracy of plus or minus 5%. Thus, this approximation should be reasonable. In addition, when one considers significant figure rules of addition and subtraction, the change is often negligible when compared to the initial concentration value. X, the proton concentration, is now easily calculated when compared to a quadratic calculation. So let's check our assumption of the 5% rule and see if the change is less than 5% of the initial concentration. And it is, only 1.3%. Now we can convert the proton concentration to the pH. Note the log sig fig rule. When taking the log of a number with 2 sig figs, one must report 2 sig figs after the decimal point. Now let's calculate the final pH of the solution after 10 milliliters of sodium hydroxide is added. The hydroxide ion is written as a reactant here because it will combine with the most acidic proton in solution, which is the exchangeable proton of acetic acid, to afford the neutralization product water and acetate. Next, let's write down quantities of acid and base given directly under the species so we can stay organized. Then convert given quantities to millimoles. Often, it is easier to work with millimoles when compared to very small numbers in moles when examining the stoichiometry of a reaction, which is what we will do here and on all subsequent examples. The 1 millimole of hydroxide will react completely with the 5 millimole of weak acid to afford 4 millimole acetic acid and 1 millimole of conjugate base per 60 milliliter total volume, which are now easily converted back to molarity. At this point, our pre-equilibrium calculations are complete, and we are now ready to look at our equilibrium concentrations after indicating expected change. Our expected equilibrium concentrations are placed into the expression for Ka. The denominator and numerator is simplified due to the 5% rule. The concentration of protons is calculated, followed by the pH calculation. Alternatively, one could use the Henderson-Hasselbalch equation to solve for the final pH. After all, the Ka, the initial concentration of conjugate base, and the initial concentration of acid are all known. The Henderson-Hasselbalch equation also gives the resulting pH of 4.15. A quicker way to solve using the Henderson-Hasselbalch equation is to stop at the step in the pre-equilibrium calculation which affords millimoles of reactants and products initially present, which is afforded after the stoichiometric calculation. Dividing millimoles by the total volume of the solution and then placing those concentration ratios into the Henderson-Hasselbalch equation, we see that we can cancel out 60 milliliters within both denominators and quickly calculate the final pH. This shortcut demonstrates that we can simply plug quantities of millimoles calculated in the pre-equilibrium step directly into the Henderson-Hasselbalch equation to even more quickly calculate the final pH. Now let's add 25 milliliters of sodium hydroxide to acetic acid. Again, we first calculate millimoles of acid and base present, have them react to afford millimoles of acetic acid and conjugate base, which are now easily converted back to molarity to finalize our pre-equilibrium calculation. We are now ready to look at our equilibrium concentrations after indicating expected change. Our expected equilibrium concentrations are placed into the expression for Ka. The numerator and denominator are simplified due to the 5% rule. The concentration of protons is calculated, followed by the pH calculation. Or simply plugging our pre-equilibrium concentrations into the Henderson-Hasselbalch equation much more easily affords the final pH of the solution. But we previously learned that we can take an even more simplified approach by plugging in millimoles of acid and millimoles of conjugate base to afford the pH. Upon closer examination of the pre-equilibrium calculation, one notices that millimoles of acid equal millimoles of conjugate base, which will simplify within the Henderson-Hasselbalch equation. Thus, when millimoles of acid equal millimoles of conjugate base, we are halfway to the equivalence point, and the pH is simply going to be equal to the pKa of the weak acid. Now let's add 50 milliliters of base. Again, we first calculate millimoles of acid and base present, have them react to calculate millimoles remaining unformed, which are now easily converted back to molarity to finalize our pre-equilibrium calculation. However, in this case, we have no millimoles of acid left, which indicates we are at the equivalence point in the titration. At this point, the only species in solution is the unstable reactive conjugate base, acetate, and it will do what it can to stabilize, which means reacting with water to convert back to acetic acid, and in the process generate an increase in hydroxide concentration. Recall we stated previously that the conjugate base of acetic acid, which is acetate, is unstable or high in energy and therefore reactive, or one could simply say it is a strong conjugate base, and we know this due to the small value of Ka for acetic acid. So let's indicate the new equilibrium between acetate and water to afford acetic acid and hydroxide, which will require a Kb for the new equilibrium. The Ka for acetic acid is easily converted to a Kb for acetate when we recall the relationship Ka times Kb equals 1 times 10 to the minus 14. And again, it is a good idea to write the equilibrium constant over the equilibrium arrows. With our pre-equilibrium calculations completed, we can now focus on our equilibrium calculation, which will include the initial concentration of acetate at T0 and the change in concentrations when at equilibrium. Our expected equilibrium concentrations are placed into the expression for Kb, the denominator is simplified due to the 5% rule, the concentration of hydroxide anion is calculated, followed by a pOH calculation, which is then converted to a pH. Alternatively, once the hydroxide concentration is calculated, it can easily be converted to a proton concentration, followed by a pH calculation. At this point, please take a moment and look over how all the sig-fig rules within these calculations were followed. In the next calculation, 60 milliliters of strong base is added, which means after calculating millimoles present, we have excess hydroxide ions in solution that can be converted to a molarity utilizing the total volume. The 5 millimoles of acetate will produce some hydroxide ions. However, the concentration of hydroxides produced within the equilibrium of acetate and water will be negligible when compared to the 9.1 times 10 to the minus 3 molar hydroxide present. At this point, the pH can be calculated one of two ways, which were demonstrated within the previous calculation, starting from the concentration of hydroxide. The following table summarizes milliliters titrant added and resultant pHs. Often your instructor will ask you to graph this data, which is a nice way to visualize this data and clearly see several interesting trends. For example, that the weaker the acid being titrated by a strong base, the higher the pH at the equivalence point. In addition, as an exercise to review and reinforce this material, it is suggested that the student do the pH calculations after 40 and 75 milliliters of the 0.1 molar sodium hydroxide are added to the 50 milliliter aliquot of 0.1 molar acetic acid, and check to make sure your answers match the data in this table.